Hello, welcome to our course on Introduction to Cryptology, lecture 2 of the first week. In this lecture, we will study modular arithmetic, but before that we study division. We already know what is division, but we will study that again and see some salient points. Our starting point is the set of integers z, which is 0, 1, 2, 3 onward, and on the negative side -1, -2, -3 and so on. Now, let x and y be two integers, that is to say x y belongs to z, then we say that x divides y if there is another integer q such that y is equal to q plus x. I write it here, y equal to q plus x. If this happens, then we say that x divides y, and we write symbolically as x and a vertical line and y. Now, let us go one step forward. This is quotient and remainder. Now, suppose we have two integers x and y belonging to z, that is a set of integers. Now, we know that we can write y equal to q times x plus r, that is we know that we can find two integers q and r such that y equal to qx plus r. This is nothing new, because we know that suppose we have got x equal to 12 and y equal to, let us say 7. I am sorry, let us move it the other way around. So, x equal to 7 and let us say y equal to 15, then we know that the usual division goes like this: 7, 15 and 7 2s are 14, then 1. So, I can write 15 equal to 2 times 7 plus 1. So, in this case my q is 2 and r is equal to 1. We also know that we can always manage q in such a way that r falls between 0 and x minus 1, that is in this case we know that this r, and if I fix x, then this r is always going to be between 0 and 6. This is not surprising, we know this. Now, this thing is written as symbols in this way. Now, there is a name for r, it is called remainder after division by x, and there is a name for q, it is called the quotient, and we give another name, we say that r is y reduced modulo x. So, here in this example 15 let us say 1 is 15 reduced modulo 7. So, if I divide 15 by 7, then the remainder is 1, and I force the remainder to be between 0 and 6. I write this as a symbol 1 is equal to 15 mod 7. This is a single entity 15 mod 7, which I write over here, r equal to y mod 7. Now, next step, we also know what a greatest common divisor between two integers is. So, suppose we have got two integers x and y, greatest common divisor of x and y is written as GCD of x and y, and it is a positive integer by definition, which divides both x and y, and if we have any other integer dividing both x and y, then definitely that integer is going to divide GCD of x and y. So, let us look at an example. For example, let us come here. So, suppose x is equal to 24 and y is equal to 10. Now, we would like to find out the greatest common divisor of 24 and 10. For that, we will have to start like this. We take 24 and then divide it by 10 first. So, I am writing here in a different way. We will see that this way is easier to handle in some in our context, but we know that in school arithmetic we do like this. We take y and then we write 24, we divide this. So, I have got 20, this is 4, and then I take 4, we do this. So, I have got 2, this is the remainder, and then we divide 4 by 2. So, I will have 2 2s are 4. So, I have got nothing, I have got no remainder. So, I come to this step, 4, 2 divides 4, and we know that this is the greatest common divisor of 24 and 10. So, GCD of 24 and 10. Now, there is a surprising fact, we can say something more with greatest common divisors, and that is this. If we have two integers x and y, then there exists two more integers r and s, such that rx plus sy is equal to GCD of x and y. Now, we will say, how do we know that? There is an algorithm for computing r and s and GCD, which is called the Euclidean extended Euclidean algorithm. We are not going into details about extended Euclidean algorithm, but we will see how to find these coefficients r and s, and that is here. So, we have already seen that these steps are true. 24 is equal to 2 times 10 plus 4, 10 is equal to 2 times 4 plus 2, 4 is equal to 2 times 2, all right. So, I know that GCD is 2. Now, what about r and s? We can run the calculations backward. If we run backward, then we get something like this. Let us see, we have got 2 over there, this is 2, we can transpose this term to the other side. So, we will get something like this, 2 equal to minus 2 times 4 plus 10, and then I can replace 4 by looking at this term. So, 4 equal to 24 minus 2 times 10, and you have got 10 here. So, minus 2, 4 is equal to 24 minus 2 times 10 plus 10, and this gives me minus 2 times 24, and here it is plus 5 times 10. We come over here. So, my r is minus 2 and s is 5, and that is what we set out to find Rx plus Sy is equal to the greatest common divisor. This was the background. After this background, we come to the topic of today, that is called modular arithmetic. Now again our starting point is z, and we denote the set of positive integers by z superscript plus. Now we choose a positive integer m. Once we have chosen an m, we say that an integer x is congruent to another integer y modulo m if m divides y minus x. That is to say, in symbols I will write x is congruent to y mod m I will put a bracket here later on, and if this happens, then I say that I write this if m divides y minus x. It is needless to say that if m divides y minus x, then m divides x minus y. Therefore, if x is congruent to y modulo m, then y is congruent to x modulo m. We will be always writing like this. We will put a bracket over here, to which is not written over here, but later on we will be careful. Why do we put a bracket here? To distinguish between r equal to x mod m and x congruent to y congruent to x mod m, or x congruent to y mod m. This means that m divides y minus x, but if I write x mod m, that means I am reducing x modulo m, that is to say that I am dividing x by m and then taking the remainder. Arithmetic over Zm. Now what is Zm? You give me an m, it can be anything, it can be 2, 3, 5, 4, whatever. I can always construct a set of 0 to m minus 1. So if you give me 5, I will construct the set 0 to 4. So let me write it as an example. So if you give m equal to 5, 5 is of course a positive integer, then I can always write z subscript 5, which is 0, 1, 2, 3 and 4. And now I define an addition. So what I do is I take any two integers in Zm. In this case it might be Z5, so something between these two, 0, 1, 2, 3, 4, and once I do that, I will add them as integers and then reduce modulo m. So that is exactly what I am doing over here. So I am taking x, and here this sum is a little different. So I am writing a plus, I am tagging it by m. So once I tag it by m, I see that I can basically write x plus subscript y, then I can write equal to x plus y mod m. I now know what is x plus y mod m. Just take the addition, divide by m, take the remainder. Once I do this, I call this result sum modulo m or addition modulo m. I can do exactly the same thing with multiplication. If I do that, so I am now considering elements in Zm. I am taking x multiplication modulo m, y, which is simply ordinary multiplication, then you reduce it modulo m. So, you are pushing it back to z sub m, that is exactly what we are doing here. And we have to note something more, that if we have no confusion about m, and when we are doing lot of calculations, then we are not going to write that subscript, we are just going to write plus instead of plus subscript m, and we will write nothing in place of multiplication modulo m, we will just write x y, that is what we are going to do. So, as an example, let us look at this. So, I can take, suppose my x is 1 and y is 2, then what is x modulo 5 y, this is 1 modulo 5 2, well this is 3 reduced mod 5, but that is 3. So, we see that is a case where x addition modulo 5 y, that is same as x usual addition y. So, sometimes modular addition is going to give me the same result as the usual addition, but of course sometimes not. We can easily find out a scenario like that. I mean, for example, if I take 3 plus 4, it is going to give a pretty large number. So, if I take x equal to 3 and y equal to 4, then I am going to get 3 plus modulo 5 4, which is by definition 7 mod 5, and which is equal to 2, because if I divide 7 by 5, the remainder is 2. Now, there are several properties of modular addition and modular multiplication. We will list these properties, we have to know these properties, and we can check these properties on our own with small numbers. So, let us see what properties are there. So, we can always check that if we have two numbers between inside Zm, that is between 0 and m minus 1, their sum, the modular addition modulo m is of course going to be inside z sub m, and then we have something called associativity, that is x plus y plus z is going to be x plus y plus z, and then we have commutativity, that is x and y in Zm. So, x addition modulo m of y is going to be y addition modulo m of x. These are very easy consequences, or these are easy properties basically. So, and at the end there are two interesting properties. One is extremely easy, because we say that we have 0, we will always have 0, because we will always have this one. So, if I add any x to 0 or 0 to x modulo m, I am going to get x. And the last one, that if you give me an x, I can find out, I can compute m minus x, and then if I add them, this is going to be 0 modulo m. Why? It is very natural. So, let us take an example over here. So, let us take 3. So, if you give me 3, so let us suppose my x is 3 now, and the modulus is 5. So, I compute m minus x, which is equal to 5 minus 3, which is 2. Now, see, if I add 3 modulo 5 2, I get 5 mod 5, and if I divide 5 by 5, the remainder is 0. So, I am going to get 0. This particular quantity m minus x is called the additive inverse of x modulo m. We will sometimes be writing just minus x without thinking much, understanding that minus x has to be put inside Zm. We now come to the properties of multiplication modulo m. Now, again the multiplication modulo m is closed, that is to say, if I take two integers x and y in m, Zm, then if I product them modulo m, of course I am going to get another integer between 0 and m minus 1. That is not difficult to see. We can check that over here. So if we have, let us say, let us take 3 and 4. So, I will get 3 multiplication modulo 5 4. So, this is 12, and of course, this is reduced mod, well, what 5, and so it is 2. It is of course inside. I made a mistake. No, I did not make a mistake over here. So, it is of course 2, and of course, this is inside z sub 5. So, that is all right. And then associativity, commutativity, existence of identity. So, let us look here. So, associativity is of course x times y times z is equal to x times y times z. Commutativity we know is x modulo multiplication modulo m, y is going to y multiplication modulo x, and here it is going to be there is 1 over here. This 1 works as the identity in the sense that if you take modulo, if you multiply 1 modulo x, if you multiply 1 and x with multiplication modulo m, you are going to get x and the other way round. And lastly, we have a property which connects addition and multiplication modulo m, which is this, that is x addition modulo m y multiplication modulo m z is going to be x multiplication modulo z plus modulo m plus, and then we have got y multiplication modulo z, and is other way round. Finally, we come to this question that how do we compute multiplicative inverse in Zm. First of all, what is a multiplicative inverse? We might have certain numbers in Zm. Let us look at this Z5. For example, I have got 2, and if I multiply modulo 5 3, I get 6, if mod 5, so it is 1. What does it mean? It means that we have got a, when we are given a number in 2, number in z mod z5, I have got another number 3 such that their product is going to be 1. But this is not always true. Let us consider where the modulus is 4. So, z sub 4 is 0, 1, 2, 3, and now let us take x as 2. Now, we can multiply 2 by all the other integers here. So, 2 modulo 4 0 is of course 0, then 2 multiplication modulo 4 1 is 1, 2 multiplication modulo 2 is, now this is 4, 4 mod 4 is going to give me 0, and 2 multiplication mod 4 3, this is going to be 6, which is mod, if you do mod 4, this is I made a mistake over here, this is going to be 2, and this is going to be 6 mod 4, that is going to be 2 again. So, always we do not have inverses, but sometimes we have inverses. Now, our question is that when do we have an inverse? Suppose the greatest common divisor of x and m is equal to 1, there exist r and s belonging to z such that Rx plus Sm is equal to 1. This is something that we have seen with the greatest common divisor, because 1 is the greatest common divisor of x and m, and if you have that, we can write Rx equal to 1 minus Sm, and therefore, what I can do is that I can reduce R modulo m. So, I get Qm plus R mod m into x equal to 1 minus Sm, and then I can take x times Qm over here. So, on the other side, so I will ultimately have R mod m x plus 1 is equal to 1 minus m s minus qx, and therefore, if I reduce modulo m, I will get R mod m times x is equal to, is congruent to 1 mod m. So, I can say here that R mod m modular multiplication modulo m of x is going to be 1. Not only that, I can where R times x plus s times y is equal to 1, which is sorry, it is not y, it is s times m is equal to 1, where GCD 1 is the GCD of x and m. So, one thing is clear here, that if the GCD of x and m is 1, then you will get another integer in Zm such that that integer, let us say y times x, is going to give you 1. On the other hand, if you have an integer x inside Zm whose GCD to m is not 1, that is d, something that is greater than 1, then we have a sequence of argument like this. I have got x times m by d. So, what I am doing here is that I have got x times m by d. I know that d is the GCD, so d divides m, so it is an integer. This is equal to x times x by d times m, and I know that this is an integer because d divides x also, because d is the GCD, and this is congruent to 0 mod m. Therefore, we can say that x wait a moment, yeah, m by d is equal to 0, where m by d is inside z sub m, of course. And now, suppose if possible x has an inverse, that means suppose there is an integer inside Zm such that y multiplication modulo m x is 1, then I can multiply this equation both sides by y. So, I get something like this, y multiplication mod m into x multiplication mod m by d, and here I can use the associative law of modular multiplication. So, I will write something like this. That is exactly what I have written over here, exactly what I have written over here, but this is nothing but 1 multiplication modulo m by d, well this is equal to m by d. Yeah, so I have started from here, I can always do this, but this is equal to y multiplication mod m of 0, which is 0. This forces m by d to be equal to 0, but this is possible only if m equal to 0. So, the calculation steps are over here. So, if I multiply both sides by y, then one use of associative law gives me m by d equal to 0, and which is a contradiction. Therefore, I come to the conclusion that an element x inside z sub m is invertible, that is it has another element such that the product multiplication modulo m is 1 if and only if the greatest common divisor of that element with m is 1. So, we stop here. So, in this lecture we have covered something called complete system of residues modulo m, which is essentially Zm that we have been dealing with, modular addition and modular multiplication, properties of modular addition and modular multiplication, and probably most importantly the computation of multiplicative inverse in Z sub m. So, that is all for today. See you in the next lecture.